In this short video, I'm going to introduce the concept of smoothing. So in machine learning, one of the tasks that we'll very commonly are trying to perform is to estimate either the conditional probability of an outcome given predictors or the expected value of an outcome given predictors. So here, I'm denoting that with E of y given x. So that's what we're going to estimate. In this particular data set that I'm showing you, which is actually a real data set, it's data from microarrays. I'm comparing two samples in an MA plot. Y is M, X is A. And we see a nonlinear dependence of Y on X. And as we'll learn in future videos, actually in the bioconductor course, is that we need to normalize this data. And to do that, we have to find this curve, this dependence, so we can remove it. So that's the motivation for this particular example. So we see this data and we think there's an underlying curve, and then there's random noise around that curve. And we have a suspicion, there's reasons to believe that this bias is actually a smooth function of x. All right, so we want to estimate y given x, and the standard approach when we have two variables of using linear regression is not going to work here. We see the regression line that's been fitted to this data, and we immediately see that there is a bias. We have at the beginning there's more positive residuals shown in green, and in the middle there's more negative residuals shown in purple, and then there's at the end again some green residuals. That's because the underlying curve appears to be nonlinear. It's more like a check mark shape. So the idea of smoothing is based in a way in Taylor's theorem that tells us that if you look at any function, no matter how complicated it is, if you look at it close in small little intervals, it could be approximated with a lower degree polynomial. So in this case, I'm assuming that if you look at a small enough window, you can assume that they has a mean constant. So the purple points in this small little interval, they almost appear as if there is no dependence of y on x in that very small window. We're assuming that the function, the underlying function, expected value of y given x, is constant in this small interval. So we do that for other intervals as well. Here's another interval where we see that the mean shifts. It's now a little bit lower. So now the idea behind bin smoothing, for example, is to move the center of these bins across the entire range of x and estimate that mean and keep that mean as the estimate of E of y given x. So we can see that we're almost tracing the curve that in our minds is the curve that should be there. That's what bin smoothing does. Now when we look at the final result of bin smoothing, it looks a little jagged. It's not as smooth as at least I was hoping it to be. Now that's because this approximation of using a constant in a small window is not always appropriate. The data is moving too fast. We have to make the windows too small, and then we have too few points to obtain up to precision of our estimates. So local weighted regression, which is nicknamed LOES, is a method that instead of fitting constants, it fits lines or parabolas. And it has other properties, like it tries to remove outliers, but the main one is that we fit lines to small windows. Now we don't have to make the windows so small because, and this is actually something that Taylor's theorem tells us, if the degree of the polynomial is bigger, we can actually expand the window a little bit. So you can think of this as forming an edge in gardening, where you want to form a curve, and you have a shovel that is straight edge, but you can form curves with straight edges, and that's what we're going to do here. So you fit a line to these windows, and then you move the window along, and you get another fitted line, and you keep the center of that line as an estimate. And here's an animation showing us how that works. And now it's giving us a fit that is much better looking than the bin smoother, in part because we're now using bigger windows, more data, more precise estimates. And at the end, we get a nice looking curve like this that appears to have captured the bias, and we can remove that bias away and improve our data. Now, what if the data is multidimensional? So here's an example. Now the expected value of y of given x comma x2, so 2 dimensions, is shown here. Now I'm not showing you data, I'm actually showing you the expected value, the conditional expectation of y given these two variables x1 and x2. So color means higher values. So sorry, blue means lower values, red means higher values. So that's we're showing you that function. We want to estimate that function with data. So here's some data, and we have from this data we now want to estimate that underlying expectation that we don't know we want to estimate. So here again we can use the same ideas. We can form small windows, and in that window either estimate a plane or a constant plane or maybe a parabolic curve, and we do it for several locations. We can do it there. We can actually do it for every single location and obtain an estimate. In fact, if we do this, we're doing something very similar to k-nearest neighbors. Right? So here's k-nearest neighbors with 50. We estimate the mean value by taking votes across zeros and ones. So that data that I showed you originally, the points were red meant 1 and blue meant 0. So in this particular case, we're basically voting for either red or blue, but then we get a proportion of reds, proportion of blues, and that proportion is shown in this plot as an estimate of E of y given x1 and x2. And you can see that it does a pretty good job, just this very simple approach of k-nearest neighbors. But again, the idea is to look at smaller bins where we think the data is closer to either constant or a plane or a simpler polynomial that we can fit, and then move that window around to obtain an estimate of the more complicated curve. So that's smoothing, a very short introduction to smoothing, and that should help us better understand some of what we do in other machine learning techniques.